So welcome to lecture number 17. And last time we asked, does real number with multiplication has inverse or not, right? So let's check. Let's choose a number a that belongs to this real number. Now let's say that a is equal to, let's say, 2. Okay. Now what has happened? When a is multiplied with a inverse, the answer must be identity, right? And what is identity in real number? With respect to multiplication, we know identity must be 1. In the last lecture we said, with respect to addition, identity is 0. With respect to multiplication, identity is 1. So identity should be 1. It means here this equation can be written as a multiplied with some number a inverse must be 1. Our a is 2 and this 2 belongs to our real number. Any number we choose should come from this set. So 2 multiplied with a inverse must be 1. Now what should be the value of a inverse? That we have to see. Well, 2 into what number is 1? Well, it is 1 by 2 equal to 1. So 2 cancel and 1 equal to 1. So our a inverse equal to 1 by 2. Now we ask, does this number belongs to this set R? Real number? Well, yes, it does. Real number contains this number 1 by 2. Now you have to remember one thing. The one thing is, identity is global property of an algebraic structure. It means for all element identity is always same. If our algebraic structure is a comma plus, so no matter what the set is, identity element is always 0 for every element, for all element that's come from this set. If our binary operation is multiplication, then for all a that is coming from a, identity is always 1. For all element it is 1. For all element here it is 0. But inverse is local property. What does local means? It means if we have an algebraic structure, let's say G comma star, and we choose an element a that is coming from this G, then a inverse for this a will be, let's say, a inverse 1. If we choose another element b from the same set G, b, then it has a inverse 2, but this a inverse will be different from a inverse 1. It has a inverse 2. What I am trying to say, inverse is local property. Every element of this set has a different inverse, but for every element have same identity. So identity is global property. It is 1 for all. Inverse is local property. So now we have axioms. The axioms are closure, then associativity, then identity, and then inverse. Based on what axioms and algebraic structure satisfies, we give them name. For closure only, we say it is magma. For closure plus associativity, we called it semi-group. For closure, associativity and identity, all three together, we call it monoid. And for all these together, this all 4 property if satisfies, we call it group, right? Now there is one last property. It's called commutativity. If a group satisfies all these 5, we called it commutative group, or other name is Abelian group. Abelian. Okay, Abelian group. What is commutative? We know it. If there is algebraic structure G comma O, operation O, where operation is defined as, let's say, G cross G to G, then commutativity says for all two element AB that we choose from this set, AOB equal to BOA. That's all. If O is plus, then it means A plus B equal to B plus A. That is commutativity. So we have four different kind of structure: magma, semi-group, monoid group, and Abelian group. 5 different algebraic structure we saw based on what property they satisfy. So these are the examples of algebraic structure. Okay. A theorem, not a theorem, but an observation. Observation is, if there is a group GO, okay, let's say GO is a group, and say there is another group H comma with another operation star is a group. And what is group means? Group means it satisfies all 4 property: closure, associativity, identity, inverse. So this group also satisfies all those 4 property. This group also satisfies all those 4 property. Here set are different. G could be different kind of set, H could be different kind of set. Here it could be another operation, here is another operation. Both are group. Now, what is the power of algebraic structure? It says, let T be a theorem on G comma O. Let's say T is some theorem that we make, and that theorem is true for this group GO. Then T is also true for H comma star. We have to remember this. This is very powerful. We don't have to check, we don't have to prove the same theorem for this group. If we prove this theorem for this group, this theorem is also true for this group. Doesn't matter what the operation is, the theorem holds. Okay? It's a very generalization concept. Any theorem that is true for this kind of a structure is also true for this structure. Okay? But a theorem true for group is not true for magma. They are different kind of object. Group and magma is different. But a theorem for magma is true for another magma. A theorem for semi-group is true for another semi-group. Okay? So now the power of algebraic structure is we are free of this proving theorem for different group. If we have G, let's say, if G, H, K all are group, then any theorem about G must be true for H and K also, and all other group. Okay? Now we have definition here. What is an algebraic structure? So let S be any non-empty set. The set should be non-empty. It means it should contain elements. So let S be any non-empty set, and star be any, let star be any binary operation defined as star, which is from same set S, Cartesian product S with S, then S embedded with this operation star is called an algebraic structure if it satisfies following axioms. If it satisfies any of following axioms, any of. What are the axioms? If it satisfies closure, it is algebraic structure. If it satisfies closure and associativity, it is algebraic structure. If it satisfies closure, associativity, identity, it is also algebraic structure. If it satisfies all four, it is algebraic structure. If it satisfies commutativity, these all five, it is algebraic structure. For algebraic structure, it is not necessary that it should satisfy all these five axioms at once. No, we saw it. If it satisfies only closure, it becomes magma. If it satisfies 1 and 2, it becomes semi-group. It is if satisfies 1, 2, 3, it is called monoid. If all these four, group. If all these five, Abelian group, commutative group, right? So algebraic structure is this one. But this is a very narrow definition, okay? It is not complete. Why it is not complete? Because we are seeing this from a different kind of, our algebraic structure is a very special. See here, right? It has a one set, one operation. Okay, it has one set, one operation. We are going to extend this idea, this kind of algebraic structure. We are going to extend this. What we have a set and operation. We are going to extend this to the idea, why only one operation? We can have two operations. Okay, so maybe a set with two operations, O and star, maybe two operations, right? This is a very generalized idea. Okay, now this is also an algebraic structure, and it should satisfy certain axioms too. Okay, now based on what kind of axiom this satisfies, okay, this structure, S some operation O, some operation star, based on what kind of axiom this satisfies, we have name for it. It could be either ring or it could be either field. Field is more powerful than ring. We have to see this. Okay, field is more powerful than ring. What is field? Field can help us to do arithmetic. Field can help us to do all arithmetic, which is plus, minus, multiplication, division, everything you can do in the field, right? In ring, you cannot do division and division, okay? I'm not going to explain what are those axioms for ring and field, okay? A very, or maybe I can tell you about this, okay? Now, a ring, first we have to specify what this O and a star is for ring and for field. So these operations are mostly a set, an operation addition, and an operation multiplication. So this is the structure, an algebraic structure, a set equipped with two operations. This is called ring if it satisfies, let's say, some axiom A1, list of axiom A1. If it satisfies axiom A2, this same structure we call it field. Okay, so field has different axioms, ring has different axioms. Okay, but the structure is same, a set with two operations, addition and multiplication. Okay, maybe I can tell a little bit about what are those axioms. I'm not going to explain everything because this is not about teaching ring and field theory. So I will give just a general example. What is ring? So a ring is a set R with an operation addition and multiplication such that this addition operation take two elements R, we know this what it is, and produce R. Multiplication is defined in the same way, which is R cross R to R. R is not real number, it is just a set, it can be any set. Now what are those axioms? Well, a ring, this set with plus must be Abelian. That is the first. This plus should satisfy, it should become Abelian group. It means it should satisfy all those 5 properties: closure, associativity, identity, inverse, and commutativity. So plus has these all axioms. It should become Abelian. What about R with equipped with multiplication? Well, it should satisfy closure, it should satisfy associativity, it should have identity. Okay? Now, this is called monoid. Okay? So R dot should be monoid and R plus should be Abelian. Okay? Now, there is one more property, which is distribution, which says for all element A, B, C coming from this set R, A dot B plus C is AB plus AC, or A plus B dot C is AC plus BC. Okay, this is distributivity property. If all this holds, it's called ring. Okay, it's called ring. Now what is field? A field, a set, some set F, same operation, addition and multiplication. Now what are the property of, what is addition? It is same F cross F to F. What is multiplication? It is same F cross F to F. Now this F equipped with addition should become Abelian group. This is the first axioms. It should be Abelian. It means all those 5 property: closure, associativity, identity, inverse, and commutativity. And this F with multiplication should also satisfy closure, associativity, identity, inverse, and commutativity. So it is also Abelian group. Both are Abelian. In ring, the one is Abelian, the other is, well, it should be the ring with multiplication should satisfy closure, associativity, identity, and one more property, commutativity. So it is called commutative monoid. So here R plus is Abelian, R dot is commutative monoid. Here F plus is Abelian and F dot is also Abelian. And the one last property is same distributive property for field 2. If this hold, F plus Abelian, F dot Abelian, and this distributive property, it is called field. What is ring? For ring, R plus should be Abelian, R dot should be monoid, commutative monoid, and distributive property. So they are different kind of structure. Okay. All field are ring, but not all ring are filled. Why? Because see, this ring with multiplication has no one property, which is inverse. So it is less powerful than this. If it will be inverse here, it will be Abelian too here. So both Abelian and distributive becomes filled, which is this structure, right? So we have filled and ring. Now in the next lecture, we will generalize this idea more in a more different kind of way by equipping a different set and structure. Okay.